Today, we're going to continue looking at implicit differentiation. So implicit differentiation is just us using the chain rule to find dy dx. The main thing that we have to get is that when we have an expression like x to the fourth, and we want to find the derivative with respect to x, when we do the apply our derivative rules and write 4x to the third, this is the derivative with respect to x. So right when we go from x to the fourth to 4x to the third, we treated x as the variable, and so 4x to the third is the derivative with respect to x. We didn't need the chain rule. We could think about using that we have used the chain rule by saying that we have to multiply by the derivative of x with respect to x, but the derivative of x with respect to x will be equal to 1. So from that point of view, we're always using the chain rule. But we definitely have to write the dy dx when I have an expression like y to the third. If I want to take the derivative with respect to x of y to the third, when we write 3y squared, that's the derivative with respect to y. So the chain rule says we have to multiply by the derivative of y with respect to x. In another context, or in another problem, here I have x to the fourth times y to the third. I need to read this as two things that are related to x being multiplied together. So we're going to use the product rule. In this case, the first is x to the fourth, and the second is y to the third. The derivative of the first is just 4x to the third. We're trying to find the derivative with respect to x. So the derivative of the first, when we write 4x to the third, that's the derivative with respect to x. But when we find the derivative of the second, when we write 3y squared, that's the derivative with respect to y. So we have to multiply by dy dx because of the chain rule. 3y squared is the derivative with respect to y. So we have to multiply by the derivative of y with respect to x. Then we just follow the product rule, take the derivative of the first times the second, plus the first times the derivative of the second, and then probably we should clean this up. Once we have taken the derivative with respect to x, we should solve for dy dx. So what we're doing in implicit differentiation, find dy dx, or take the derivative with respect to x of all the terms, and then solve for dy dx. Find the derivative with respect to x of all the terms, and then solve for dy dx. Let's use this process, excuse me, let's use this process to find the equation of a line tangent to a curve at a given point. In this case, instead of having a function where y is equal to f of x, I've got an equation defining the curve. Y squared is x squared over xy minus 4. It's a mix of x's and y's. When we want the equation of a line, we need two things. So to find the equation of a line, we need two things. We need a point and a slope. We want to find the equation of a line. We need two parts, a point and a slope. We want to find the equation of the line tangent to the curve at the point 4, 2. So we've already got our point. That part is given to us. To get the slope for a tangent line, we use the derivative. So first, we're given the point. That's the first thing that we need. And second, we need to find a slope, which is given by the derivative. In this case, to find dy dx, we're going to use implicit differentiation. A couple of ways we can go about this. I see y squared is equal to x squared over xy minus 4. When we first look at this, we might think we can use the quotient rule, where we have the top and the bottom. And then for the derivative of the bottom, we're going to need a product rule with this xy. So instead of using the quotient rule, I want to think back to when we first started finding derivatives with shortcuts. If we can write terms, then we should write terms. So recall. Instead of using the quotient rule, if we can write terms, then we should write terms. This will help us avoid the quotient rule. So if y squared is x squared over xy minus 4, I'm going to multiply both sides by xy minus 4. So my equation becomes y squared times xy minus 4 is equal to x squared. Now I'm just going to multiply the y squared and write this as xy to the third minus 4y squared is equal to x squared. Now we can avoid the quotient rule. We're going to have to use the product rule in xy cubed, but we were going to have to use the product rule anyway because of this xy. And that product rule would be inside of a quotient rule, and that sounds like a mess. So we think back to the beginning. If we can write terms, then we should write terms. Now I can use implicit differentiation. I'm going to take the derivative with respect to x of all these terms. So the derivative with respect to x of xy cubed, which is going to need a product rule, minus the derivative with respect to x of 4y squared, which is just going to be a chain rule question. And this will be equal to the derivative with respect to x of x squared, which is the most normal term in this equation. So now we're going to go through and take the derivative, remembering to use the chain rule if we use the power rule with a y factor. And remember that x and y are y and x are related, so I have to use the product rule in xy cubed. So I'll need the product rule here. So since I've run myself out of space, need the derivative with respect to x of xy cubed minus the derivative with respect to x of 4y squared equals the derivative with respect to x of x squared. So for xy cubed, I've got a first. The first is x. And then the second function will be y to the third. So the derivative of the first is just 1. And the derivative of the second will be 3y squared times dy dx because of the chain rule. 3y squared is the derivative with respect to y. So the chain rule says multiply by the derivative of y with respect to x. So that the derivative of the first term is just going to be 1 times y cubed plus the first, which is x, times the derivative of the second, which is 3y squared times dy dx. That was just for that first term, the xy cubed. Next, we're going to need the derivative of 4y squared. When we write 8y, that's the derivative with respect to y. So the next thing will be minus 8y to the first, but that's the derivative with respect to y, so we have to multiply by the derivative of y with respect to x because of the chain rule. On the other side of the equation, the derivative of x squared is 2x, and we're looking for the derivative with respect to x. 2x is the derivative with respect to x, so we don't need the chain rule there. Or the derivative of the inside is 1. Now that we've gone through and done the derivative with respect to x all the way through, we need to solve for dy dx. So we're going to keep the dy dx terms on one side and move the non-dy dx terms to the other side. So now we solve for the dy dx. So the dy dx terms stay on one side, non-dy dx terms on the other side. I'm going to rewrite this dy dx term as 3x y squared times dy dx. And I'm going to subtract this y cubed from both sides. So I keep the dy dx terms on the left, non-dy dx terms on the right. Next, we can factor out the dy dx. And now it's dy something times dy dx is 2x minus y over y to the third. So then we'll divide by the coefficient of dy dx. So we know that we need a point and a slope. We have a point 4, 2 that was given. The next thing we need is the slope. And since it's the slope of a tangent line, we're going to use the derivative to get it. So we need to find dy dx. Now that we have dy dx, we can just plug in the point that we care about. Let's evaluate this dy dx at the point 4, 2. So x is 4 and y is equal to 2. So 2 times 4 minus 2 cubed over 3 times 4 times 2 squared minus 8 times 2. So 2 times 4 is 8, 2 cubed is 8. And in the bottom we have 12 times 4 is 48 minus 16. The numerator is 8 minus 8, so saved from having to know what 48 minus 16 is. 30 something, I think. Now we just need to put all this together into the equation of a line. The equation of a line is y equals y naught plus m times x minus x naught. So my point is 4, 2, so y naught is 2. My slope is 0 times x minus x naught, which is 4. So the equation of a line is y equals 2.
Wait, Professor, so it's just a straight line?
Tangent line is always a straight line. This is a
horizontal line.
Yeah.
Okay.
So the tangent line is horizontal. Let's take a look. Oh, I deleted it already. Dang it. I hate when I set something up and then I close the tab that I had the thing set up in. So our original curve was y squared is equal to x squared over xy minus 4. Oops, I didn't want decimals. Oh, it's not showing me a graph. Dang it. So if we had some other point on the curve, then we can just plug that in. We can get a different value. We should notice that there are some points that might be on the curve, and we might end up with vertical slope. So dy dx might be vertical at some points on the curve. Any questions? Okay, so in this case, this is very different than the problem that we did yesterday. Yesterday, we were looking at the circle x squared plus y squared equals 9. So we could solve for y, but we end up with 2 different functions to get the full circle. We could write y as a part of the curve. We could write as a function of x. But in this case, we can't. We'd have to figure out some way to solve this cubic y cubed minus xy cubed minus 4y squared. We would be kind of stuck in trying to solve this for y. So implicit differentiation was called for in this example. Any questions?
Can we go back to the next page? Notes.
Yeah, we had several phases. So here, in the first part of this page, we were finding the derivative with implicit differentiation. So that's what this phase was about. And then once we had the derivative, that's when we can plug in the point to find the derivative at a point. Any questions? Comments? Snide remote.
Can you explain what those variables mean? Like what? I mean, y(o).
Oh, so this right here is the point slope. This is the equation of a line. Containing the point x naught, y naught. With slope m. This is what y equals mx plus b looks like when we have a generic point rather than the y-intercept. So when we write the equation, it's a more general form of y equals b plus mx. So b plus mx is the equation of a line through the point 0b with slope m. This is the same thing if but if x naught is equal to 0 and y naught is equal to b, we have the same thing. So what all we're saying here is that x naught is 0 and y naught is equal to b. When we write variable x with a subscript of 0, that means that we have a particular value of x. So x sub 0 or x naught will be like our starting value of x. Any questions? Right. A lot of times when we when we talk about lines, a lot of times we almost exclusively work in y equals mx plus b, or better, y equals b plus mx. It's a great place to start, but a lot of time we just kind of stop right there. So we don't think about how we start equations in different places. So this x minus x naught business should be, well, maybe should be emphasized more. So there are certain things that we recognize. If I write the equation x squared plus y squared is equal to 9, we know that this is a circle centered at the origin with a radius of 3. If I have a circle where the center is moved to some other point, so this circle has a center at the origin, with a radius of 3. So this point will be at 3, 0. This point will be at 0, 3. If I happen to have a circle where the center is somewhere else, let's say x naught, y naught with a radius of 3. Then I still want the same form, x squared plus y squared equals the radius squared. But if I want to move the center to x naught, y naught, I just move the center this way. Replace x with x minus x naught and y with y minus y naught. And now we have a circle with the center at x naught, y naught with a radius of 3. This happens in functions as well. So if we consider the function y equals x squared, we know this is a parabola opening up with a vertex at 0, 0. If I replace the x with x minus x naught, now my center is at x naught, 0. And if I replace y with y minus y naught, now I have a parabola with vertex x naught, y naught. Normally, we won't write it in this form, y minus y naught equals x minus x naught squared. What we would do is write y is equal to y naught plus x minus x naught squared. When we add and subtract, we perform a shift on the graph. Adding and subtracting performs a shift on the graph. If we perform addition before a function happens, we'll make a horizontal shift. If we perform addition after a function happens, then we perform a vertical shift. So if we start off with our function with our parabola with a vertex at 0, 0, if I trade my x for x minus x naught, I'm doing addition before the function happens. We take x minus x naught, then we raise to the second power. So that's going to be a horizontal shift. When we then add y naught afterwards, this plus y naught happens after the square, so that's going to produce a vertical shift. So this is how operations perform, when we perform operations in conjunction with a function. So we either do operations before the function or after the function. And if we do addition, that'll produce a shift. If we do multiplication, that will produce some kind of stretch. Any questions?
Professor, so
Okay.
for like the circle one, I'm still kind of confused as to why you can't just insert like the x naught and y naught into the equation.
I'm not sure. What do you mean? My point is that if we have when we have the equation x squared plus y squared equals 9, this is a circle with the center at the origin with a radius of 3. If we change the equation to have x minus x naught squared, that moves the center of the circle. So
Oh.
this is everything within 3 units, or everything 3 units away from the point where x and y is 0. So this is everything 3 units away from the point 0, 0. This equation represents everything that's 3 units away from the point x naught, y naught.
Oh, okay, that makes sense. Because I thought it was still doing implicit equation, so I was kind of confused. I was like, I just didn't understand what you were writing. But
No,
now I
it
understood
has to
it.
do with the difference between this function y equals b plus mx and y equals y naught plus m times x minus x naught. This is the less, we don't see lines written in this form very often, but it is kind of better moving forward.
That's the point slope equation, right?
Yeah.
Okay.
Sometimes point slope is written as y minus y naught equals m times x minus x naught, which I don't really favor because it doesn't look like a function, and the equation of a line, we tend to want it to look like a function.
Yeah, I'm just kind of not familiar with like point slope equations, so I'm sometimes like I had a problem on like the homework where it requires me to use this, but I wasn't sure how to.
Yeah. This is a common thing because when we go through our algebra class, we learn about these like two different forms of equations of lines: point slope and slope intercept. And then out of context, we're like, well, why would we need two? Let's just go with slope intercept all the time. It's easier for me to check because I just have find a slope and an intercept, and so it's easier for me to grade. So I'll just have everybody write slope intercept. But it doesn't necessarily make any sense if x represents the number of years after 1900. I don't want if x represents years, I don't want to have to plug in the entire year for my variable x. So if I have a function that's modeling, say, the population of a city in any given year, I don't want my input to be just the year, because then this y-intercept would be the population of the city in year 0, and maybe the city did not exist in the year 0. So we move the starting point over to something more useful, like say the city was founded in 1875. I would put x minus 1875, or just say x is the number of years since 1875. So we're just changing the inputs with all this addition and subtraction. It's just shifting things left and right.
And is that why you were able to represent x as 0? Because you're just shifting the x?
Where am I saying x is 0?
Y equals 2 plus 0 times x minus 4.
I'm not saying x is 0, I'm saying m is 0.
Well, so you solve for y there, so you must have had to substitute x for 0, right?
Whatever I pick for x here, once I multiply by 0, I didn't plug in anything for x. 0 times whatever we plug in here, we're always going to get 2. I'm not substituting x equals 0, m is 0, and since this is multiplication, that term just goes away.
Professor Lich?
Yeah.
I have a question. So this one is the slope intercept or point slope? This
Which one?
the one you just explained right now.
This is point slope,
Okay.
and y equals b plus mx, that's slope intercept.
Oh, okay. Point slopes. Got it. I write it down now. Thanks.
Because this one has a slope and the intercept, and this equation involves the slope and a point x naught, y naught.
Oh, that's the point. Got it. Thanks.
Any questions? How's everybody okay? Everybody looks stunned.
Professor Rich, so when do we know to use point slope or intercept slope? Did you explain?
Depends on what you have. In this case, we had a point that wasn't an intercept. The point that we had was 4,2.
4,2, got it, okay.
I don't know what the intercept is, so I'm not going to use the slope
Yes,
intercept.
it makes sense, got it. Thank Professor Rich, I understand.
Any other questions? How's everybody okay? All right. This is one of the things that we just have to get used to, is like moving equations around. We also have to get used to reading expressions so that we can see what's going on. I think I'm probably talking about this operations before and after a function, because that's what's going on in my trig class right now. And all my classes always just kind of like bleed into each other. Once I started teaching trig, I started thinking more about moving stuff around with shifts and stretches. But that's all part of a more complicated pre-calculus class than is practical for our purposes. Any questions? All right, so that's going to do it for today. We did more review of implicit differentiation, and we did an example where we found the equation of a line tangent to a curve at a given point, a classic question in calculus. In this case, we were given a point and we just had to find the slope. This is a problem that we've done before in various forms. Find the equation of the tangent line. You need a point from the function and a slope from the derivative. In implicit differentiation, that means the slope from dy dx. Any questions? Comments? Snide remarks? All right, that's going to do it for today. I will see y'all on tomorrow. Everybody have a good day, and thanks for playing.